Welcome to section 3.3. Today you're going to get a crash course in differential geometry. We're going to talk about arc length, curvature, and then on your own you're going to read about the unit normal and binormal vectors. And together those vectors form a famous coordinate system called the TNB or Frenet frame. And if you go on in math, you will learn about that later. So in this box here, I've got two formulas, arc length and arc length parameter with base point A. We're going to be using this formula. I like just writing the length of r prime of t, but you could do this too. This just spells it out. And then the arc length parameter with base point A, the second formula you use to reparameterize a curve in terms of arc length. And there's many reasons you'd want to do that. Arc length is an intrinsic property of a curve, whereas t, if you think of t as time, that's not intrinsic. So moving on to this example, we want to find the length of the curve for t going between 0 and ln2. Now over here in the picture, you see I've got a line, and if you eliminate the parameter on that curve, you just get the line y equals 3x. So we don't even need an arc length formula to do that. We could just use the distance formula. D is the square root of the difference in the x coordinates, 4 minus 1 squared, plus the difference in the y coordinates, 12 minus 3 squared. And that's square root of 3 squared is 9, and then 9 squared is 81, so that's the square root of 90. Okay, but let's verify that with our arc length formula. So we're going to need an r prime, all right, so that's easy, 2e to the 2t, comma, 6e to the 2t, and we're going to need the length of r prime, because that's what we're going to integrate, all right, so that's the square root of 2e to the 2t, quantity squared, plus 6e to the 2t, quantity squared, which is the square root of 4e to the 4t, so you have to square the 2, and you have to square the e to the 2t. E to the 2t squared, you multiply the exponents, that's 4t. So that's plus 36 e to the 4t. So we get the square root of 40 e to the 4t. And now we can take the square root of 40, which is 2 root 10. And we can take the square root of e to the 4t, which is e to the 2t. So that's the expression we need to integrate. So the arc length is the integral from 0 to ln2 of 2 root 10 e to the 2t dt. All right, when we integrate, that 2 goes out, and we get root 10 e to the 2t between 0 and ln2. Moving over here, that's root 10, factor that out, and then we've got e to the 2 ln2 minus e to the 0. E to the 0 is 1. Now to do e to the 2 ln2, I'll do my scrap paper over here. That's e to the ln4, because you bring the 2 up as an exponent, and that's just 4. So we've got root 10 times 4 minus 1, which is 3 root 10. And that's the same as the square root of 90. Same answer. No surprise there. Okay, moving on to the unit tangent vector and curvature. You've already done some homework problems that involve the unit tangent vector. It's just the tangent vector divided by its length. That's what makes it unit. Now, curvature measures how much a curve curves. And if you look at these three pictures here, we can all agree that this one right at this corner is curving the most. But how do you measure that mathematically? And the way you measure it mathematically is you check how much the unit tangent vector moves per unit distance. And that would be, it's called kappa, and it's the length of dt ds, where t is the unit tangent vector. Now that requires parameterization by arc length, which is actually kind of difficult. So fortunately, we've got two go-to formulas that are super easy. This is the one I use the most, and there's some cases where you use this one. In fact, you have one homework problem that uses that one, and I warn you in the instructions to use that one. Otherwise, you're going to use the top one. So let's do an example where we find the unit tangent vector and the curvature kappa. So we've got a helix here, and for the unit tangent vector, we're going to need r prime, which is negative 3 sine t, 3 cosine t, 4. We're going to need the length of r prime, which is the square root of, if we square out, this, the minus sign is going to get squared out, so this would be 9 sine squared t plus 9 cosine squared t plus 16. Now, hopefully you can do this in your head. This is going to be 25, the square root of 25. But let me just show you the part you would do in your head. If you factor out a 9, you get sine squared t plus cosine squared t. Now that's 1. So that's why you have 9 plus 16. So that's going to be the square root of 25, which is 5. Okay, now we can form the unit tangent vector, big T, that's r prime divided by its length. We've got r prime right here, and we divide each component by 5. So that gives us negative 3/5 sine t, 3/5 cosine t, comma, 4/5. So that's the first part, finding the unit tangent vector. Now we want the curvature, kappa. Now kappa is the length of t prime over the length of r prime. So we already have the length of r prime, that's 5, but we're going to need the length of t prime. So first we're going to need t prime. So t prime of t is negative 3/5 cosine t, negative 3/5 sine t, comma, 0. So the length of t prime is the square root. Again, the minus gets squared out. 9 over 25 cosine squared t plus 9 over 25 sine squared t. Factor the 9 over 25 out. Cosine squared plus sine squared is 1. So that's the square root of 9 over 25, which is 3/5. And so now kappa, moving back up here, we've got the length of t prime, that's 3/5. And we want to divide by the length of r prime, that was 5. And so that's 3 over 25. So that's the curvature. Notice the curvature is constant. It doesn't depend on t. And that's because if you look up at this helix here, you're going around and around in a circle in the xy plane, and then you're just pulling it up. It's kind of like a slinky, but the curvature on the curve stays constant. Okay, let's do one more where we use the second formula. We want to find the curvature at t equal 1. And in this box here, I explain why we want to use the second formula, not the first formula. All right, so we're going to need, looking at this formula here, it looks like we're going to need r prime of 1, r double prime of 1, and the cross product. So let's just start taking derivatives. R prime of t is negative 2, 2t, 3t squared. R double prime of t is 0, 2, 6t. So r prime of 1 is negative 2, 2, 3. And r double prime of 1 is 0, 2, 6. All right, so let's take the cross product. R prime cross r double prime. I'll leave off the at 1 just for efficiency here. I, j, k, negative 2, 2, 3, and 0, 2, 6. All right, first component is going to be 12 minus 6, which is 6. The second component will be negative 12 minus 0, but then it's negative. Remember, the second component is negative, so this will be positive 12, and the last component will be negative 4. And you should pause the video and make sure you can verify those numbers. All right, so now we need the length of that vector. The length of r prime of 1 cross r double prime of 1 is the square root of 36 plus 12 squared is 144. And then negative 4 squared is 16. That's the square root of 196, which is 14. And we still need, for that formula, we still need the length of r prime of 1. So r prime of 1 in length is the square root of 4 plus 4 plus 9, which is root 17. So kappa at 1 is, we want the length of the cross product on top, r prime cross r double prime, and then the length of r prime of 1 quantity cubed on the bottom. So on the top we get 14, and on the bottom we get root 17 cubed. So that's 14 over 17 to the 3/2. I like that, but your homework, I believe, will ask for a decimal, and that's 0.1997, I think. Okay, and that's the end of the ones I'm going to do. You're going to read on your own about normal and binormal vectors, and here are the formulas. Normal is super easy, and binormal is too. It's just the cross product of n and t. All right, and that's the end.